Hello, we are working on solving systems of linear equations with two unknowns and two equations. We are going to look a bit at the geometrical interpretation of the process of finding the solution of such a system. Imagine the system we have has the equations 2x minus y is equal to -1 and x plus y is equal to 4. Each one of those equations represents a line, and those are the two lines I have graphed here. I did rewrite the equations in the gradient intercept form, just for the ease of graphing them. And the first equation gives me the equation y equals to x plus 1, so it's another way of writing the same information, and the second one gives me the equation y equals minus x plus 4. When I write these two equations in any of those forms as a system, so with this bracket over here, what I'm saying is I'm trying to find what are the values of x and y that will make the two equations to be true at the same time. In this case, we can graphically see that that's happening where we find the point of intersection of the two lines. So that point that, according to the graph, looks like having x coordinate 1 and y coordinate 3. This is just from the graph. This point 1, 3 has a property that it verifies both equations. So when I'm trying to solve a system, what I'm trying to find is the point of intersection between the two lines. But it's not always true that two lines intersect at a point, and that's why I want to look at other examples of other possible situations. I'm going to keep the first one of the equations, so I'll leave the line that I sketched there, but I'm going to change the second equation, so I need to add something else to my picture. So let's say that now my system, so system number 1, now system number 2 is 2x minus y is equal to -1, same equation as the first one from the previous system, and 2x minus y is equal to 1. Now, the system is saying that I want 2x minus 1 to be equal to -1, but I also want 2x minus 1 to be equal to 1. And that sounds like something that should not happen. Let's write the second equation. Sorry, this is a y. Let's write the second equation on the slope-intercept form. So we'll be saying that we want y to be equal to 2x minus 1. So if I try to sketch the graph of this line, this is a line parallel to the one that I already have, but with y-intercept -1. So let's add the line over here. So this is y equals 2x minus 1. Now, what are we trying to do? We are trying to find the point of intersection of those two lines, and there is no such a point of intersection because the lines are parallel, so they do not intersect. So L1 is parallel to L2, no solution. So this is a very different case from the first one. Remember that in the first one, what we got was a solution at the point 1, 3, and this is what we call a unique solution. Well, because there is only one of them. So on the first case, I'll add the picture very small here. We had a sketch where we had two lines that intersect, and we found the solution as a point of intersection. On the second one, the lines are parallel, so there is no solution because the lines do not intersect. We still have one more case to consider. Again, I'm going to keep the first one of the equations, so 2x minus 1 is equal to -1. And then my new equation is going to say 4x minus 2y is equal to -2. Let's make space for this new picture. Well, also here there is something special happening, because you may notice that the second one of the equations can be obtained from the first one just by multiplying by 2. This means that both equations have exactly the same information. So we don't actually need to have the two of them, because having both doesn't add anything. We could just write the first one and we will be given the same information. So there is only really one equation. We could try, if you are not convinced, we could try to sketch the line corresponding to the second equation. So I'm going to isolate y, so I'm going to say that 2y is equal to 4x plus 2, and then I'm going to divide by 2, so y is equal to 2x plus 1. So no surprise here. This is actually the line we already had. So now what does it mean for a point to be a solution of this third case? It means that the point verifies the equation 2x minus y is equal to -1. So the point verifies the equation of the line. So it means that the point belongs to the line. So that means that we have infinitely many solutions. And those are all the points of the line. And we can write how those points look like. We know that when we consider a value of x, then to belong to the line, the value of y has to be 2x plus 1. So this is one way of writing how the solutions look like. X such that is a real number, and then we consider the pairs x, 2x plus 1. On the other hand, if we want to write the solutions in terms of y, so we fix the second coordinate with any real number y. So we need to isolate x for y, so I can do it over here, need a little bit of space. Y minus 1 over 2 is going to be equal to x. I'm just isolating x. So the solutions can also be written as the form y minus 1 divided by 2, comma y. And what we have in this case is that the two equations represent the same line. And those are the three cases that we can have. We can have a unique solution, we can have no solution, we can have infinitely many solutions. And these different cases of intersections of lines on the plane are the geometrical interpretation of the possible solutions for all 2 by 2 system of linear equations.